Okay, so here we're going to look at both sections 24.4 as well as 24.5. So now we're going to look at a spherical surface and we're going to look at refraction. So in other words, at a spherical interface between two optical materials with two different indices of refraction. This is directly applicable to some real optic systems, just like the human eye. It's also a stepping stone for analysis of lenses, which usually have two spherical surfaces. So in this particular figure here, we've got a spherical surface with radius r. That forms an interface between two materials with indices of refraction NA and NB. So out here, NA, the index is less than what it is here. So the surface forms an image point P prime of an object P. And we want to find how the object and image distances are related. So the center of curvature is on the outgoing side of the surface, so R is considered to be positive. Ray PV strikes the vertex V and is perpendicular to the surface at that point, passes into the second material without deviation. Ray PB, making an angle alpha with the axis, is incident at an angle theta sub A with the normal, in other words, the normal being perpendicular to the surface here, and it's refracted at angle theta sub B. So in other words, it comes in here, we've got a normal to the surface, and it is coming in at this particular angle. When it gets refracted, it gets refracted at this particular angle here. These rays intersect at P prime at a distance S prime to the right of the vertex. So the figure is drawn for the case where N sub B is greater than N sub A. The object and image distances are both positive. All right. So what we're going to do is we're going to go through some proofs here. We're going to say that theta sub A is equal to alpha plus phi. So in other words, this and this are going to be equal to this. And we know that phi is going to be equal to beta plus theta sub B. If you remember the law of refraction, remember that the ratio here of these indices and whatnot, you can also take the tangents of these particular relationships, just like we did with the lenses, the mirrors before. So again, we can approximate both the sine and the tangent of an angle by the angle itself because reasons. And then the law of refraction ends up simplifying magically into this particular relationship. If we combine this bit of magic with what we see up here, we end up with this. And we substitute this into the equation here for 24.8. Then we're going to end up with this particular relationship. Again, we're going to use the approximations here that the tangent of alpha is equal to alpha. Again, small angle, about the same. Yeah. And we're going to ignore it in these equations. And magically, this junk becomes this junk. And then finally, we substitute these equations into equation 24.10, divide out the common factor of H, and we come up with this, the refraction at a spherical surface. All right, so to obtain the lateral magnification for this situation, we use the construction here, 24.21. We'll draw two rays from point Q, one through the center of curvature and the other through the vertex. once it goes through, this gets refracted this way. When this goes through, it just goes straight through since it's normal to the surface. So it goes straight through. Build yourself a virtual image over here. Using some trig and the law of refraction, we also say for small angles, yeah, sure, this is true. We come up with this particular formula. So all of the problems here are sort of worked through in, they're going to use those types of approximations in order to be able to boil things down to a simple formula. So equations 2411 and 2412, which let's see if we can pinpoint those. This one and this one, which look somewhat similar to what we've had before, but they're not exact. These provide, can be applied to both convex and concave refracting surfaces, provided that you use the sign rules consistently. It doesn't matter whether NB is greater than or less than NA, but it does say that constructing the diagrams where N is negative and this is less than that, use them to derive that for these particular cases. So that's really kind of what we're looking at here for these particular types of problems. If R ends up being infinity, then we end up with this particular relationship. We can kind of see that from looking at, let's see, this particular formula right here. If this were to go to infinity, this term would fall to 0. So for this particular case, we end up finding that in this particular case, that the lateral magnification ends up being 1. In other words, the image formed by a plane refracting the surface is always the same size as the object and is always upright. So a familiar example of image formation by a plane refracting surface is of if you take a straw and you look at it this way, or a canoe paddle, when viewed from some angles, the object looks like it has a sharp bend because the submerged part appears only to be about 3/4 of the actual distance below the surface. So now let's go to 24.5. All right. So the most familiar and widely used optical device after the plane mirror is going to be the lens. I mean, for those of you that wear glasses, this should not come as a surprise. A lens is an optical system with 2 refracting surfaces. The simplest lens has 2 spherical surfaces close enough together that we can ignore the distance between them. And this is what we call a thin lens. So we can analyze a system in detail by using the results of the previous section for refraction by a single spherical surface. But we're going to postpone this so that we can first discuss the properties of thin lenses. So the focal point of a lens. We see this particular figure that shows a lens with 2 spherical surfaces. This type of lens is thickest at its center. The central horizontal line is called the optic axis, no surprise there, as with spherical mirrors. So the centers of curvature of the 2 spherical surfaces lie on and define the optic axis. So in other words, it's like you've got a surface here that would have your focus here, and then you would have another one here, which ends up producing a focal point over here. So the optic axis passes through the centers of both. So you can see the rays coming in here and then eventually converging here at this particular point. The focal length is measured from the lens center. It's always the same on both sides of the lens. And for a converging thin lens, F is going to consider to be positive. So if we have light that is reflected out from this particular point, they go through this particular lens, and they can end up becoming parallel. So when a beam of rays parallel to the optic axis pass through, then the ray, well, you've seen all of that. A bundle of parallel rays incident on the lens shown in figure 24.26, like this, converges to a real image point after passing through the lens. And this type of lens is called a converging lens. Its focal length is a positive quantity, so it's also called a positive lens. We're already using, we've already used the concepts of focal point and focal length for spherical mirrors. The two focal lengths in figure 24.26, both labeled F, are always equal for a thin lens, even when the two sides have different curvatures. And we'll look at that a little bit later on. So now let's take a look at this here. This shows us how we can determine the position of the image formed by a thin lens. So we're going to use the same notation and sign rules as before. We're going to let S and S prime be the object and image distances respectively. And we're going to let Y and Y prime be the object and image heights. So ray QA, parallel to the optic axis before refraction, passes through the second focal point here. After refraction, ray Q O Q prime passes undeflected straight through the center of the lens because it is at the center of the two surfaces and it's parallel and very close together. There is refraction when the ray enters and leaves the material, but no net change in the direction. So if we look at the triangles here, we can come up with these relationships. Since we know, or the reason for the negative sign here is that the image is below the optic axis, and then Y prime is going to be negative. The two angles theta beta are equal, and the two right angles of right triangles there are similar. So therefore, we can start throwing this together. Or we can turn and rewrite it as this. We now equate these two equations divided by S, and rearrange the resulting equation to obtain this. This analysis also gives us the lateral magnification of this as well as this. So if we take a look at this particular figure, we can show how a lens forms a three-dimensional image of a three-dimensional object. The real thumb points towards the lens, and the thumb's image points away from the lens, just like what we saw before. So in contrast to the image produced by a plane mirror, this image is, in fact, not reversed. So it's not quite the same thing as what we saw before. The image of a left hand is, in fact, a left hand. However, the real index finger points up, while the image points down. So the image produced by the left hand is, in fact, inverted. As you might expect from what we saw up here, where this was positive and this was negative, this image is being inverted here. So to make a real hand match the image produced by this, you would simply rotate the hand by 180 degrees around the lens axis, and then you've got what you had originally. Inversion of an image is equal to a rotation of 180 degrees around the lens axis, okay? So let's say we have a bundle of parallel rays incident on the lens in this figure. When they come in and they look and go through this diverging lens, what happens is, rather than them being focused in on one particular area, they're actually focused out. And if we do a back projection of this, we can come up with a second focal point. Its focal length is a negative quantity, and the lens is called a negative lens. So the focal points of a negative lens are virtual focal points, and they are reversed relative to the focal points of a positive lens. second focal point, F2 of a negative lens, is the point from which rays that are originally parallel to the axis appear to diverge after refraction. So incident rays converging towards the first focal point emerge from the lens parallel to its axis. So that's what this is trying to reflect. If you had rays coming in that are not parallel to the diverging lens, then they become parallel. And it looks like these are trying to converge at this particular focal point. So you can see that these two equations apply to both negative and positive lenses. Various types of lenses, both converging and diverging, are listed here. Any lens that is thicker in the center than at the edges is a converging lens with positive F, and any lens that is thinner at the center than at the edges is a diverging lens. So the thin lens equation, we're going to start with a general problem of two spherical surfaces, two spherical interfaces, separating three materials with indices of refraction Na, Nb, and Nc, as shown here. And the object and image distances for the first surface are S1, S1 prime, and for those on the second surface are S2 and S2 prime. We're going to assume that the distance between the two surfaces is small enough to be ignored in comparison with the object and image distances. So S2 and S1 prime have the same magnitude, but opposite sign. So if the first image is on the outside, outgoing side of the first surface, then S1 prime is positive, but when viewed as an object from the second surface, it is not on the incoming side. So we can say that this relationship holds. Using the single surface equations, we can come up with this particular relationship. Again, this is not something I'm that concerned with you being able to derive. All of the notes are there. The thin lens equation, or the lens maker's equation, which is what you see up here, these are going to be the important results out of all of this. So you can see here all of these particular units being put together and how you can determine each of these variables depending on what information that you do have. So again, what you're seeing here is the curvature here, the radius of curvature for these two lenses being put together. You've got the rays that are emanating from Q end up producing a virtual image over here of Q prime. And since this is converging, it's considered to have a positive focal length.